Hi, and welcome to the Worldwide Center of Mathematics. Today on our series, we're doing the Top Pop Math Chops, which are a series of mathematical proofs and little fun bits of math. And today we're looking at the proof for the area of a circle, which is the area inside of a circle. So to start off, we look at, we approximate the area with a square within the circle. Notice here the square's diagonal is the same as the circle's diameter. So looking at this cuts the square in half, which gives us a 45, 45, 90 triangle. And knowing the properties of a 45, 45, 90 triangle, we can find the lengths of the side of the square. So as we know, the area of a square is a side squared. So this approximation gives us that the area of the square within the circle is 2r squared, which we know is less than the actual area of the area inside of a circle. So next we're going to look at we're going to approximate the new area with a hexagon. So looking at the hexagon within the circle, we can tell it divides into 6 equilateral triangles, which can help us determine the area of the entire hexagon. So to find the area of one of these equilateral triangles, we have to look at 1/2 times the base times the height. And knowing that this is an equilateral triangle, we can tell that when you divide, well, we can figure out what the lengths of the base are. So each of these 6 triangles are equilaterals, and then when you cut them in half looking for the height, it gives you an angle of 30 degrees. Up here when you split it, and then 60 degrees for the other angle. So with the 30, 60, 90 triangles, you look at the properties, and the properties of a 30, 60, 90 triangle are as written. So we know these are equilateral triangles, so we know that every length of the triangle is the same. So this radius is also going to be the base of the full triangle. So this x here is going to be half of the radius. And so we now know the full base, that's pi, the radius. Looking at the radius, not pi. And so the full base is going to be the radius, full base of one of these triangles. And now if we know x is r over 2, so we now know the height of this triangle is square root of 3 times r all over 2. Now knowing the height of each of these triangles and the base is just the radius, we can find the area of the entire hexagon. Plugging it in and solving it through, we find that the approximation of the hexagon using using this hexagon to approximate the area of the circle gives us 2.59 radius squared, which is what we also know is less than the actual area of a circle. So our third method will be to use an n-sided polynomial within the circle to approximate it. So with that, I can kind of draw more lines, but it's you'll have to think about it yourself. And so these are all more triangles. It's going to be an n-sided polynomial, so just imagine n going to infinity, and then we can look at what the area would be then. So again, the area is going to be however many sides the polygon has times the area of one of these individual small triangles. And as n goes to infinity, those triangles get very, very small. So again, it's going to be the base times the height for each of these triangles. But once we know the base and the height, you can kind of reformat the formula, so you want to look at how many sides there are times the base, which will give you the full perimeter of the n-sided polygon. And then here, NB is now the perimeter of the polygon, and as n increases, it becomes closer and closer to the approximation, the exact approximation of the area within the circle. If you just think of tiny infinitesimal pieces of triangles. And so NB would be the perimeter. And so this formula now is, we have to look at this perimeter, and Archimedes back in 200 BC, he used this constant pi, which he looked at as the relationship between the circumference and the diameter, the ratio. And so the polygon perimeter is the circumference of the polygon, which gives us a better idea of the circumference of the circle. And so to find a way to plug pi into this formula, he had the circumference, but he was dividing this by the diameter. So we had to multiply by the diameter to get this base formula. We also know the height is still going to be the radius of the circle. So here we can see that pi is the ratio between the circumference and diameter, and then 2r will be the diameter. So multiplying those two will just leave us with the circumference, which we had here, NB, and plugging in r for the height, because we know that once these triangles are small enough, the height of the triangles will be the exact radius of the circle. And so simplifying, this formula, you get the equation we now know and love of the area within a circle, which is pi r squared. Thank you for watching our video today, and subscribe for more videos, and look at the rest of the playlist and tell us which is your favorite proof or tidbit, and any suggestions you would like to see. Thank you.